Hello everybody, welcome back to AP Stats. This is Unit 4, Lesson 5, where we're talking probability distributions, random variables, the expected value, standard deviation, these things called DRVs and CRVs. We are cramming a lot in today's lesson, so let's break it down and start off with these first couple of essential questions that we want to know. How can you display a probability distribution, and how can you find the average outcome of a chance process? Well, the first thing we need to do is describe these ideas of what are known as random variables. Random variables are something that numerically describes the outcomes of a chance process. We've got two different types. There's discrete and continuous. Discrete random variables take a fixed set of possible values with gaps in between them. To see what a discrete random variable looks like, let's consider this chance process, and that is tossing a coin. But we're going to do more than toss a coin one time. We're going to actually toss it 3 times, and we want to see what's the distribution of all possible outcomes. Well, we know we can get heads 3 times. That's heads, heads, heads. We can also get heads 2 different times. Now, those heads can come on the first tosses, they can come on the last tosses, or they can come on the first and last toss. So those are all the different ways that we can get 2 heads. Now, what about all the different ways that we can get 1 heads? It's going to be heads, tails, tails, or tails, head, tails, or tails, tails, heads. The heads coming on the first, second, or third toss is all the different ways that we can get 1 heads in a coin toss. And then finally, we can also have 0 heads in your 3 tosses. Now let's go ahead and recognize that there are 8 different possible outcomes in this setting. We want to create a probability distribution for the number of heads in these 3 coin tosses. Now this is going to be an important point. We're going to let x be the random variable representing the number of heads. And this is important because we want to see that capital letters are going to usually represent these discrete random variables like this, or any random variable really. So x is going to be the possible number of heads, and we know that they were 0, 1, 2, or 3 heads, and we want to write out the probability. Well, 0 heads occurred exactly 1 out of 8 times, 1 heads occurred 3 out of 8 times, 2 heads occurs 3 out of 8 times, and 3 heads occurs 1 out of 8 times. If you add up all of those probabilities, you will get exactly 1, meaning we've represented 100% of all of those situations. Now, what we can also do is create a histogram that displays this graphically too. And that means we have 0, 1, 2, or 3 heads, and that's going to represent the number of heads. So our random variable is going to go on the x-axis that we see here. Now, on the y-axis, we're going to include the probability, or the relative frequency. That's the probability of x. Now, you can display this any which way you want, as decimals, percentages, or as fractions. Since I have fractions here, I'm going to go ahead and write out the fractions and put this in place. Now, I only need to go up to 4 out of 8 because when I look over here, I only had exactly 3 out of 8 as my highest probability. So for 0 heads, I'm going to have my bar sandwiching around the 0, and that was 1 out of 8 times, right? 1 heads occurred 3 out of 8 times, 2 heads also occurred 3 out of 8 times, and 3 heads occurred 1 out of 8 times. So this is a probability distribution. You can display it as either that table or this histogram. Either one shows each possible outcome and their respective probabilities, and we can use this to answer some interesting questions, such as, what's the probability of getting at least 1 heads? Well, at least is going to use this greater than or equal to symbol. Probability is going to use the capital P, right? That's going to represent probability. And the number of heads, we said that was x. So the P of x being greater than or equal to 1 can be represented on the graph as such. This is at least 1 heads, this is at least 1 heads, and this is at least 1 heads. Adding up their probabilities for each of those outcomes, looking at what they have on that y-axis, that's 3/8 plus 3/8 plus 1/8, or 7 out of 8. So that's our probability. Now, what we might want to know is something that's a little bit more interesting than this, and this is what we get into with the expected value. Okay, what you can first recognize is that, hey, this is looking like a symmetrical distribution. And I know that in the symmetrical distribution, the mean is going to be right there, or the average is going to be in the middle. And that seems like, oh, well, in 3 coin tosses, a 50-50 scenario, half of those should be heads, half should be tails. Well, what's half of 3? 1.5. But that seems weird. How can you have 1.5 heads? Well, let's check it out and see if we can't prove it mathematically that this is indeed true. Well, let's consider every possible scenario and its respective probability. 0 heads occurred 1 out of 8 times, so I want to account for that. 1 heads occurred 3 out of 8 times, I want to account for that. 2 heads occurred 3 out of 8 times, I want to account for that. And 3 heads occurred 1 out of 8 times, I want to account for that. And you notice that that's multiplying through. Okay, now what I want to do is consider all of these. And if I'm considering all of them, that means I want to combine them together, which means I'm adding them up. And if I do this, carry out the multiplication, that gives me 0. This gives me 3 out of 8. This gives me 6 out of 8. And then this gives me 3 out of 8. Okay, and so what we're essentially doing here is we are using the probability in conjunction with the actual value of the number of heads. And it's going to show us the total number of heads, but kind of averaging out over 8 possible outcomes. And we had, in this situation, 12 total heads, but over 8 possible outcomes. Now, that doesn't seem to make a lot of sense, but if you write that as a decimal, we do indeed get 1.5. And this is actually the way that you calculate what's known as the expected value. So if we were to toss a coin 3 times, we would expect to see 1.5 heads. Maybe more appropriately, we would say, if we were to do this trial of tossing a coin 3 times, many times, thousands of trials of 3 coin tosses, the average number of heads per 3 coin tosses is 1.5. And that's summarized as we look at here. The expected value, also known as the mean of a random variable, the average. So if we were to consider a probability distribution in general like this, where each value of the random variable x can be denoted with some number, and we'll call it x1, x2, x3, and a probability of x as p1, p2, and p3, respectively. To find the expected value, which we note as e of x, it's the same as this notation, mu sub x, we can say that's going to be take the respective probability, multiply it with its actual event, the value of that event. Then we're going to do that with each individual one. So P2 times X2, P3 times X3, so on and so forth, all the way until we get to the very end. The probability of the last one, the last outcome, times its value. And then we want to add them all up. Now, we can simplify this and do it in some shorthand and say that the summation of all of these things is capital sigma, that's the notation we use for summation, is equal to the probability of each individual outcome, that's P sub I, times the actual outcome itself, X sub I just standing for individual, that's all it is. Each individual probability multiplied by its respective outcome, sum them together. And this is going to give us the expected value, the average of some kind of discrete random variables probability distribution. Now, a quick mnemonic device for this is recognizing, hey, this to me kind of looks like PIXI, kind of looks like the word pixie. And so we can see that the word sigma pixie could be acting as a nice mnemonic device for the calculation of expected value. And we interpret this, and this is a super important interpretation. You can't just say the average number of heads. You have to kind of reference it as in many randomly selected individuals or many randomly conducted trials of some chance process, the average value is this. So let's go ahead and try and put this into a little bit more context by looking at this example. Suppose a homeowner spends $300 for a homeowner insurance policy that's going to pay out $200,000 if the home is destroyed by fire. Let X equal the profit made by the company on a single policy. From previous data, the probability of a home in this area will be destroyed by fire is 0.0002. We want to compute the expected value of X and explain what it means. Well, let's first make a probability distribution of this chance process. Okay? So we've got really 2 outcomes that we are concerned with respect to the company and the profit it is going to make. Right? So the first thing we want to do is recognize, okay, I'm looking at this in terms of profit, and that's going to be X. So my profit is going to be one of 2 things. It's going to be $300, or it's going to be negative $200,000. right? Those are our two possible outcomes that we have. Now, we can earn $300 if there is no fire. Okay, so the company is going to make $300 if there is no fire. However, every now and again, in very rare circumstances, there will be a fire that will destroy the home. And that means the company is going to have to pay out $200,000. So does that mean their profit is negative $200,000 in the case of fire? Well, actually, not exactly. Because we have to remember that they already got this $300. They're not giving out $200,000 to anybody. They're only giving $200,000 to people who bought one of these policies. So they've got that $300 in their back pocket, which means we have to take that out of consideration for the amount of money that they have to pay out. And really, they're only going to lose $199,700 in terms of profit. Now, that is only going to happen on a very rare setting, right? So the probability is going to be, for that instance, 0.0002, told to us at the end of the problem. Well, that's the outcome of there being fire, which means the only other outcome we're really considering is there's no fire. The home is not destroyed by fire. Well, if 0.0002 represents the probability that a home is destroyed by fire, then that means we have a 0.99998 probability that it is not destroyed by fire, just by using the complement rule. So now that we have this probability distribution table drawn out, we can use our formula to calculate the expected profit. And that is going to be E of X, which is found by using our sigma pixie formula. So I take each probability, 0.9998, and I multiply it with its respective profit, positive $300, and then I sum it up with any other ones. So the other outcome we have was 0.0002 multiplied by that losing $199,700. The negative sign is very, very important there because that's showing you are losing money, right? You're losing money on 0.0002 of these policies. How much is that in total? It is a positive $260. So that is my expected profit. So what does that mean? Well, if the company sells many policies, then on average, they can expect $260 in profit per policy. And that's what's really important here is we are looking at this in terms of per policy, not just on any one policy, right? Because in any one policy, you would say, well, they got $300 in cash, right? But what this is doing, this is something that's much, much more powerful because now it's taking into this consideration that possibility that their home is destroyed by fire. So it's a much more telling rule or much more telling calculation and statistic. Very, very powerful for us to take a look at. Because now what we can also do is start to ask ourselves, well, what if we have another scenario? Let's say if the company is selling a certain number of policies, we can then find out how much money they can expect to make, even considering how much they lose. So if they were to sell, let's say, 2,000 policies, then how much would they expect to make? They would expect a profit of 2,000 policies times that expected profit, and that's going to get you $520,000. That's how much profit they can expect just from selling these 200 policies. And what that's going to do is take into account the rare chance that they may end up having a home destroyed by fire and they still have to pay out. So very, very powerful tool, the expected value. Interpreting it is super important. Now, on top of looking at the expected value, in addition to it, we can find the standard deviation to describe the variability of a chance process. Okay? Now, there are two things that will really describe the variability. One of them is called the variance, but the variance is not super telling. It's sigma squared. What we really care about is the standard deviation, which is just sigma. So let's go ahead and define what variance is. Variance, sigma squared, is the average squared deviation of all possible outcomes of the random variable x from its mean. Now, unfortunately, that's really confusing to think about, well, why do I care about the squared deviation? We usually don't. This value is not important right now, but it will come into play later, so I want to introduce it to you. What really matters is when you take the square root of sigma squared. If you have something squared and you take the square root of it, squares and square roots cancel each other out, and you're left with just the thing. So if I take the square root of sigma squared, I'm left with sigma, which is my standard deviation, and that's the most important thing. How much a random variable will typically vary from the expected value, that is your standard deviation. And we can interpret it with this sentence starter. A randomly selected individual will typically vary from the mean by sigma. Now, the formula for this is kind of a mess. The good thing is you don't have to really worry about doing that formula because it's never really expected of you to do it. You're just going to be using a calculator to do it. So let's go ahead and take a look at a calculator and see how that might work, and especially looking at this setting. So imagine selecting a US high school student at random, and we're going to define the discrete random variable x as the number of languages that a randomly selected student speaks. So here we can see the most likely number of languages is 1, by seeing that that's got the majority of students having that number of languages that they speak. However, we do know there is some variability here. So looking at just more what's the most likely, I want to know if I have a whole bunch of students, what's the average number of languages that they would speak? We can also calculate the standard deviation and see how much variability do we see. So let's go ahead and take a look at that. This calculator that's found by rapidtables.com can be found to work with a discrete random variable distribution just like this. So the first thing that we recognize, our data number, our first entries here should be 1, and then 2, and then 3, and then 4, and we need to add a row, and that is going to be 5. So what's important about recognizing this is just seeing that, okay, these are my respective languages that are spoken. And then we enter in the probability. The first one we had was 0.63, then 0.295 for 2, and then we had 0.065 for 3 languages spoken. We had a 0.008 probability of 4 languages spoken, and a 0.002 probability of 5 languages spoken. When we calculate this, we see a standard deviation, a variance, and a mean. Okay. Now again, we don't have to show the work for this because some of these are so complicated. We just have to actually be able to interpret them. So standard deviation of 0.6709 and a mean of 1.457. Let's write that out and interpret them. I'll write it out as mu this time. Mu sub x. Again, mu sub x and e sub x are interchangeable, and that's 1.457. So we can interpret that as saying from many randomly selected US high school students, the average number of languages spoken is 1.457. So on average, each kid will speak 1.457 languages. Again, that doesn't seem to make sense. How can you speak half of a language? What it's just indicating is saying that, hey, you could be speaking more than one language. That is something we are going to typically see. Okay? Now, the standard deviation, however, sigma sub x was 0.6709. And this is where things start to get a little bit more interesting. From this, we are going to use this sentence starter here, and we'll state that as a randomly selected individual will typically vary from the mean number of languages spoken by 0.6709. Now, on its own, that still doesn't make a lot of sense. So here's what I like to do. I like to say, well, let's go ahead and add and subtract that from the mean, because that's what deviation from the mean is representing. What are we saying here? 1.457 plus 0.6709 is going to be about 2.1. So if any student speaks less than 2.1 language, we would say that's not terribly unusual. That's typical variation, a student speaking less than 2.1 languages. But this, what standard deviation does, it gives you a barometer of weirdness. And it tells me if I know a student speaks more than 2.1 languages, then they're going to be atypical. So that's why I like to look at this standard deviation. You have to look at it in conjunction with the mean to really get a full understanding. A student that speaks more than 2 languages, that's going to be kind of weird, right? But a student that speaks 2 languages, no, they're still within that typical variation. That's not unusual. More than that, pretty unusual. Now, the final thing that we want to do in today's lesson is to take a look at continuous random variables. So, continuous random variables is really going to rehash some of the things that we've already discussed. A CRV, or continuous random variable, is a random variable with no gaps between values. These variables take on all values in an interval, and we describe them using a density curve. The example that I always like to use with this is to revisit the shoe size versus the foot length example. Both of them are measuring the same thing, how big a foot is. Now, a discrete random variable would be describing it through the shoe size. Somebody can have a 10, somebody can have a 10.5, and somebody can have an 11. But there's nobody that's going to have something in between a 10 and a 10.5. There are gaps between those. However, if we were to use centimeters to measure how long a foot is, somebody might have a 25 centimeter foot, but what would be the next longest foot? I don't know. The next longest foot would be something like 25.000000, and it really can go on. There is no next longest foot. There are an infinite number of values from one value to the next in a continuous random variable. There are no gaps here. So we have to consider in that context a continuous random variable. We can't make a histogram for it because we don't know what the next value is going to be. We have to use something else, and that's a density curve. Let's see what some density curves look like. One of them might be described by using a random number generator. And we select a number between 0 and 1. We want to know what's the probability that a number is between 0.3 and 0.7. Well, a random number generator is going to say that every single number on a random number generator is going to be equally likely. So they'll have the same probability being selected. 0 has just as likely a chance of being selected as does 1, as is the same probability as 0.3. So what does that mean? Does 0.3 have a 1 probability of being selected? Well, no, that can't be, because that means 100% of the time the number 0.3 will be selected. Well, remember, with a density curve, the probability of finding something is going to be related to the area underneath that density curve. There's no width here, there's no base, there's only height, which means there can be no area for this value. For one particular number, there is no probability that that number is being selected. That seems weird. But what you have to think about is we're actually looking at, most of the time, a range. And the range there is 0.3 to 0.7. So when we're looking at this, now we can see, oh, there is a space between here. And we can see that that shape is a rectangle. And that's base times height. Well, the width of the base, or the length of the base, is from 0.3 to 0.7. That's 0.4. The height is that number 1. So 0.4 times 1 is 0.4, which makes sense for us. That's going to be about 40%. 40% of our number should be between 0.3 and 0.7. So intuitively, that does make sense. Now, not every density curve is going to be a rectangle that's so simple like this. Sometimes it's more like a triangle. Sometimes it's some other kind of weird, crazy curve. And a lot of times we work with ones that are normally shaped. So imagine a normal distribution like this. Maybe say weights of a watermelon in a crop follow an approximately normal distribution with a mean of 20 pounds, which we remember the mean goes in the middle, and a standard deviation of 2 pounds. So at each one of these marks, these inflection points represents a standard deviation. And we go up and down the line, seeing where the different weights of these watermelons will lie. Now, when we sample many, many watermelons at random from this crop, then we can consider the weight of any one randomly selected watermelon as being this letter X. And it's going to follow a normal curve. And we have to remember, well, how did we find area under a normal curve? Because this is a density curve. And if we want to find the probability of a watermelon having a certain weight, we have to look at the area underneath that curve. And we did this by doing NormCDF calculations. So NormCDF, stuff that we looked at way back in first semester, it makes a valiant comeback. And we can calculate the NormCDF of something like this. If we want to know the probability that a randomly selected watermelon X is less than 23.2 pounds, less than is going to use that symbol. Probability that a randomly selected watermelon is less than 23.2 can be found using a NormCDF calculation, where we have a mean of 20, a standard deviation of 2, a lower bound going all the way to negative infinity because I'm looking at the left-hand side here. I'm looking at less than. And then we're going all the way up to the max weight that we could possibly see that we want in this setting is 23.2 pounds. Right? We are looking at, here's about 23.2. And we are looking at everything that would be less than that. That represents all of these values here on the left-hand side. And that's going to be the area that we want. So let's go back to one of our NormCDF calculators and find that value. Type in a mean of 20, standard deviation of 2, change it to below the weight that we want, which was 23.2 pounds, calculate it. That drawing matches the shape that we drew, and we get 0.9452. So what does that tell me? That the probability of randomly selected watermelon that weighs less than 23.2 pounds is 94.52%. And that's it. So if you stop to think about what it is we accomplished with this lesson here today, we looked at discrete random variables, found out how to calculate their average values and outcomes. We learned how to interpret that value as well as calculating and interpreting the variability through standard deviation. We distinguished between discrete random variables and continuous random variables and how to calculate probability of chance events that follow either discrete or continuous random variable distributions. Thank you guys for watching. Have a wonderful day, and I will see you next time.